Log on, tune in, find out. Another good idea from Cambridge.
In this nice and cozy room, and I hope that you don't fall asleep, and I try to keep you interested. So I'll talk about the Brunn-Minkowski inequality, and I will give a version of it, a discrete version of it. So to start with, I will write one of the possible versions of the classical Brunn-Minkowski inequality. So you take two sets in Rn. So you take A and B, two sets in Rn with finite volume. And you're going to study the set of midpoints of A and B. So you choose a parameter t between 0 and 1. And the set of midpoints depending on t is the set of convex combinations of a point in A and another point in B. So it's the set of 1 minus t times A plus t times B for A in A and B in B. And now the goal is to write an inequality on the volume of M, knowing the volume of A and B. And there are many ways to write it, but the one which is maybe easiest for later generalization is the following. So the logarithm of the volume of MT is at least, well, the convex combination of the same for A and B. So 1 minus t, the logarithm of the volume of A plus t times the logarithm of the volume of B. So that's the starting point. There are many equivalent versions. So instead of writing logarithm, you have to you have a version with powers 1 over n, for instance, which is slightly stronger, but it's a consequence of that one, for more or less formally. And for generalizations, I don't want to consider the volume, the version with 1 over n, because it's not clear what n will have to be in some in more abstract settings. So I keep that one. And so interestingly, there is a similar inequality in Riemannian manifolds. So in Riemannian manifolds, you cannot add 2 points. You cannot take convex combinations without a definition. But then, if you are in a metric space, if you have a point A and a point B, and if by chance you have a shortest path realizing the distance between A and B, you can decide that a t midpoint is a point on a shortest path lying at distance 1 minus t times dAB from A and at distance t times dAB from B. So that was in Rn. So if A and B are included in a manifold, a Riemannian manifold, or actually in any geodesic metric space, we define MT of A and B is the set of points Z such that for some A in A and B in B, we have d AZ equal t dAB and dzB equal 1 minus t dAB. And this way you can generalize, or you can try to generalize, the Brunn-Minkowski inequality to metric spaces. So then, if X, I shouldn't have done that, is a Riemannian manifold, so we know what the result is in the case of a Riemannian manifold. You can still write that kind of inequality, but there is a correction term, and that correction term depends on curvature. So I'm not going to speak really about the Riemannian case, but it's just to introduce that correction term and its interpretation. So in positive curvature, the inequality gets better. In negative curvature, the inequality gets worse, because, well, if you are in a hyperbolic space, say, so with negative curvature, so you have something like that, a saddle, and you take A here and B here, the midpoints are here, and you see that the midpoints get smaller. On the other hand, if you're on a space with positive curvature, such as a sphere, and you take A here and B here, then the midpoints are something here, and it's obviously bigger. So you can write the inequality in terms of the Ricci curvature. So this is not today's focus, but if curvature is at least k, then we have logarithm of the volume of M t is at least the 1 minus t, the same convex combination as above, logarithm volume of A plus t logarithm volume of B, plus k over 2, I think, t 1 minus t dAB square. That should do it. And so you see how it behaves. It's quadratic. It's maximal when t equal 1/2, and then you get k over 8. And it has a squared second degree behavior in the distance. So the further A and B are apart, the better the inequality gets. Actually, this can be used as a possible definition of a Ricci curvature K. So it is equivalent. If you have this inequality for all A and B, then you know that curvature is at least K. This theorem was proved some years ago by some people, including one in this room, Dario. This idea lies at the heart of the approach by Sturm and Lott and Villani of a possible definition of curvature on more general spaces. But this definition, they write, suppose that you have geodesics in your spaces, like that if you have A and B, you have a curve joining them. It's not really obvious how to use it in discrete spaces because, well, for example, with this definition of midpoint, you might have no midpoint at all in a discrete space between 2 points, because the distance, for instance, can only take integer values or whatever. But then it's a problem how to adapt this kind of definition into discrete spaces. So now, today, I will present a joint work with Cédric Villani about how to try and do this in the discrete cube, which is, for me, one of the simplest examples of discrete spaces. So our original goal was to prove that the discrete cube has positive curvature in the sense which comes from the generalization of this inequality. So in the end, we couldn't do it, but we could prove something very close to this inequality, and that's what I'm going to talk about. So now X is the discrete cube of dimension n, O1, the set O1 to the n. And now you have to define what a midpoint is. So imagine that you have 2 points A and B in the cube. Well, the first thing to notice is that contrary to the case of Rn, in general you don't have, you may have no midpoint at all according to this definition, or you may have many of them. If the distance is odd, you have no midpoint according to this definition, but then it's easy to solve. You just add plus or minus 1/2 in the definition and you get approximate midpoint up to an error of 1/2. So that's not a problem. And now also you may notice that, for instance, if you take points that lie at opposite corners of the cube, then you have a lot of shortest paths between those points, and each of these shortest paths defines one midpoint. So you get a lot of midpoints. So for example, if DAB equal K is even, the number of midpoints is equal to, well, K, choose K over 2. So I still didn't give the definition of a midpoint. Well, if the distance is even, I keep the same definition, and if the distance is odd, I take any point such that these equalities are true up to 1/2. So I take any of the two possibilities on a given path. So now we have the result. So let A and B be two subsets of the discrete cube, and let M1/2 be the set of all midpoints of A and B. So with t equal 1/2, then we have a Brunn-Minkowski inequality. So the logarithm of the, well, the volume here is just the cardinality. So the logarithm of the size of M is at least 1/2 the logarithm of the size of A plus the same for B plus K over 8 DAB squared. And now I have to give the value of K, and the best value we have is K equal 1 over 2n, and n is the dimension of the cube. So in that sense, you see it's restricted with respect to the previous inequality, because first I stated it only for t equal 1/2, and I don't know how to do it for other values, which is kind of annoying. And then, well, I don't know what the best value of K is in the, we don't know in the case of the hypercube. So, although, you know, it has to be of order 1 over 2n. It cannot be 1 over n. It cannot be much better than that. Because if you take A and B to be singletons lying at opposite corners of the cube, then DAB is n, so DAB square is n square. And the number of midpoints is n choose n over 2, which is roughly at most 2 to the n. And so logarithm of the number of midpoints is at most n, and so you get that k has to be 1 over n. So now maybe I will give some elements of a proof of that. Oh, no, one more word. So I said that we cannot prove this for t different from 1/2. We can do any value of t if the sets A and B are convex. Because, well, the naive idea for doing other values of t is to decide, is to iterate the midpoint construction and say, for instance, that a midpoint with t equal 1/4 is the iteration of a midpoint and then another midpoint. But then if you do that in the naive way, you find that you end up with a point that is a midpoint of 2 points in A and 1 point in B. And then you don't want that in the inequality, except if the set A is convex, then the midpoint of 2 points in A still lies in A, and so this convex combination is really a 1/4 midpoint of 1 point in A and 1 point in B. So it's okay for any t if A and B are convex. And here I'm cheating a little bit because you remember that for midpoints in the case of odd distance there is an error of 1/2, and if you iterate the construction the errors add up, so you have some error term. So you need to increase a little bit the set of midpoints, and that's mainly technical. Okay. So for those of you who were here yesterday, you might remember that I gave another definition of a Ricci curvature for discrete sets, and I was able to compute it for the discrete cube, and you got something like 2 over n plus 2, or 2 over n plus 1 maybe, 2 over n plus 1. So it's the same order of magnitude, so it's kind of compatible, at least, in this definition. But still the original problem of taking the notion of curvature coming from the Brunn-Minkowski inequality and applying it to the discrete cube is still open, as far as we know. Sorry?
Could you repeat it?
Yeah. If you take the notion of a discrete curvature that has been defined using this kind of idea by Sturm, Lott, and Villani, we still don't know if it holds in the case of the discrete cube, because it's slightly more complicated than the one we have in the Brunn-Minkowski inequality. The main difference is here in the Brunn-Minkowski inequality, we take the set A, the set B, and we take the set of all midpoints of all points in A and in B. So you have one here, but you also have one here, and you have a lot of them, really. So something like that, and we reuse the different points at different times. So and in the definition that was made by Sturm, Lott, and Villani, first you choose an optimal coupling between A and B. So like only this point goes to this point and this point goes to this point. And then you take only the midpoints that lie in the middle of this coupling. So you get that one as well. You'll get that one as well, but you will not get the ones in the red ones. So you have, in the definition they use, there are less midpoints involved.
Can I ask this thing about convexity? I mean, if you put A equals, in the general case, if you put A equals B, do you get something interesting?
Yes, but then, well, this term is trivial, but then you still get something, yeah. But it's not difficult. The proof with k equals 0 is very easy. So you get that. It's still something, but it's not too complicated. So, well, maybe now it's time to give the proof for k equals 0. So for this, you need to understand how midpoints are constructed from a point in A and a point in B.
Excuse me, what happens if instead of having 1 and 0, you have two different numbers in each direction?
So you have a 0, 1, and 2, for instance?
No, you have A1 and A2 and A3. Then you don't have the theory.
So if you, I don't understand the question, sorry. You have a 2 and a 3, so how?
You have A1 in the real line, A2 in the real line. And instead of having 0 and 1, you have A1 and A2. What happened?
I don't know.
This is a very particular theory. You should be able to extend this to the general case.
I don't know really.
Okay.
So I'm going to talk about the case of k equals 0 first. So you have to prove that basically the logarithm of the cardinality of the number of midpoints is at least 1/2 the logarithms of the A and B. So it amounts to proving that the number of midpoints squared is at least the number of points in A times the number of points in B. So what I'm going to do is I'm going to take every pair of points in A and B and I'm going to construct a pair of midpoints from that, and I'm going to prove that this is an injection, and that way I will have proven the inequality. So what's a midpoint? For simplicity, let us assume that DAB is always even. So if for the odd case it's more technical, but it's the same. The IDs are the same. So you have, for instance, A equal 01, 01, 000, 1, 1, 1, and B equals, say, 01, 1, 0, 1, 0, 0, 1, 1, 0. And now, how do you build the midpoints? Well, everything that doesn't change between A and B, you have to keep. So here you're going to have 01. Here you don't know. Here you're going to have 00 and 11. Okay, and now there are 4 places you have to fill. And out of these 4 places, you have to choose half of them from A and half of them from B. So let's say that, for example, the first 2 places that are left I take in A, and the last remaining places I take in B. And of course, I could do it any other way, but there is an opposite way to do it, which is I do the opposite choice. So the first 2 choices I take in B, and the remaining choices I take them from A. Now, the statement is, from M and M bar, you can reconstruct A and B if you know how the choice was made. If you decide in advance that you're going to, each time you have to construct a midpoint, you have going to choose the first bits from A and the last bits from B, then if you know M and M bar, you can reconstruct A and B. And the algorithm is everything that is common between M and N bar, it's common between A and B, and for the differing bits, the first the first differing bits you encounter, they came from A, and the other one they came from B, and you can reconstruct. So AB maps to M bar is an injection from A times B to into N times M. And that's it. So it's a good place to stop if something is not clear, because I'm going to elaborate on that construction. Okay. Now, how could we improve this? Well, we still have a lot of room, because we decided to take the first choices from A and the rest of choices from B, but we could have done every other bit from A and every other one from B, etc., etc. So what's the parameterization of these choices? So if the distance between AB is equal to K, then the choice in this construction is parameterized by a set of indices from 1 to k, and so I have to tell which come from A, which come from B, and I have to take 1/2 from each. So it's parameterized by a part of 1k, of the set 1k, 1 to k, which I call a crossover, because this comes from biology maybe. So it's by a part C included in 1 to k with size k over 2. And hopefully for each of these parameters C, I get a different construction of a pair of midpoints M and M bar. So
just a question, so this you need to embed it in one end, so you read from left to right every time?
Yeah. And so a remark is that if I change C to its complement, then I just exchange M and M bar. So I denote M bar equal phi sub C of A and B, and M equal small phi sub C of AB, and M bar is equal to small phi sub C bar of A and B, where C bar is the complement of C. Now, hopefully, each of these choices of C yields a new pair of midpoints. So in the best of words, we hope that maybe all the pair of midpoints we get that way are all distinct. And then if the map ABC maps to big phi C of AB is an injection, was an injection, because it's not, then we would have an improved inequality. We would have the number of midpoints squared would be at least the size of A times the size of B times the number of choices for C. So this I'm going to denote by CK, C sub k. It's the set of parts in the set of parts in 1R, in 1K, with size k over 2. And C would be the union of the CK. And of course, here you have the choice of K, which I neglected. But anyway, it doesn't matter because the map is not an injection. So we would like to get something like that. So it's not true, but still, what we will do is we will show that we can bound the number of choices for C that lead to the same value of phi sub C of A and B. So, now, given M bar, well, it's just a pair of midpoints for now. You define by Y the pre-image of this map. So it's the set of those C's. So C, if you know M and M prime, the distance between M and M prime, M and M bar is the same as the distance between A and B. So you know C lies in capital C sub the distance between M and M bar, such that there exists A and B with capital phi sub C of A and B equal M bar. Now, if you know that, if you can prove that Y, the number of points in Y is smaller than a fraction of the number of codes C that you use, then you have the inequality we want up to a correction factor of alpha. Number of midpoints squared is at least the number of points in A, the number of points in B, and times alpha. And here I neglected because in the left case the distance is supposed to be known, and on the right I didn't. You don't know what the distance is, but you just have to decompose according to the distance in each pair and sum the corresponding inequalities, and you get that. So you just sum up over the different values of the distance between A and B or M and M bar. So now you have to prove something like that. You have to prove that if you know M and M bar, there are not so many codes C such that M and M bar are obtained from C and some point in A and some point in B. So now there is an observation, which is look at the way that M is built from A and B. So imagine that you change the code C at one position. So you move one bit, you move one element of C, you move it to another position. So that makes distance 2 in the, okay, I'm going to write it explicitly. So define, if you have two codes C, you define their distance C, D, C, C prime is equal to, well, the symmetric difference, the number of points in the symmetric difference. So that is at least 2, because you just change the position of one choice. And then, now, the coding operation is an isometry. So if you, sorry.
Maybe it's something strange, maybe 1 over alpha, because on the right-hand side, alpha, the bigger alpha, the better.
Okay, sorry. Yeah. Okay, you're right. So I was saying, if you change C prime, if you move from C to C prime by changing something, then starting from A and B, you will move M by the same amount. So if, and it's the other way around, because the way to go from AB to M bar is completely equivalent to going from M bar to AB. It's an involution. So if you have phi C of AB equal phi C prime of A prime and B prime, then the distance between A and A prime is equal to the distance between C and C prime. So that comes from the construction. Okay, and now there is a nice observation, which is,
do you assume that the distance from AB is equal to the distance from A prime to B prime, or is it?
no, it's a consequence. It's a consequence of that. Because here, phi C preserves the distance between the 2 points you get. So if here it's equal to here, then necessarily the distance from A to B is the distance from M bar is equal to A prime B prime. And as a consequence, you get A prime equal D B B prime, if I'm not mistaken. Okay, now I'm going to prove that consequence if C and C prime lie in my set Y, then the distance from C to the complement of C prime bar, is greater than the distance from A to B. Is at least the distance from A to B, because you write you have that phi C prime bar is equal to B prime A prime, and phi C is equal AB is equal to, no, sorry, it's the inverse relation. Okay, if you have I need the inverse, sorry. So you have your set Y, and you have phi C prime inverse. Okay, sorry, I'm going to do it slowly. So if you have if you have C and C prime in Y, you have M bar is fixed, so you have phi C of AB. You have AB equal phi C inverse of M bar, and A prime B prime equal phi C prime inverse of M bar. So that implies that B prime A prime equal phi inverse C bar prime of M bar. And by the isometry property, that means that the distance between C bar prime and C is at least the distance between B prime and A, and the distance between B prime and A, it's the distance between one point of A and one point of B, so it's at least DAB. So what you get is that the distance between Y and the set of complements of the C in Y is at least equal to the distance between A and B. And now we are getting closer, because what we want to prove is that Y is small. And now you have this set Y, which lies in some space, the space of parts of 1k of size k over 2. And you know that the distance between a set and its complement is large. And this means somehow that the set has to be small. And for that, you need concentration of measure. Again. So here I'm not going to give proofs of everything, but the idea is the following. So remember the set CK, which was the set of parts of 1k of size k over 2. There is a natural action of the symmetric group of size k on CK. You just permute the elements of 1ki, okay, CK. So the symmetric group acts on CK in the obvious way. Now, this action is very nice. Like all the stabilizers, all the fibers of this action have the same cardinality k over 2 factorial square, and well, it's very well behaved in a measure theoretic way, and in particular, if I know concentration of measure on Sk, I know concentration of measure on Ck. So concentration of measure means, so it's a null theorem. If so on Sk, define the metric, the distance d between a permutation sigma and sigma prime. It's defined as the number of indices at which the permutations differ. So it's the number of I such that sigma I is not equal to sigma prime I. Then you have concentration of measure in the sense that if f is a one Lipschitz function from Sk to R, then this function is almost constant, as in the yesterday's talk. So you have, there exists a value m is not a good choice. G is not a good choice. F bar such that the measure, so this is the uniform probability measure on the symmetric group, measure of those sigma such that f of sigma minus f bar is greater than t. This measure is small, and it's smaller than a Gaussian control, and I guess it's something like t squared over 2k. And this should do it. So how do I use this? Now, a consequence, if I have two parts in Sk which lie at some distance apart, then these two parts, at least one of these two parts, is small. So if I have z and z prime included in Sk, then with the same size, say, then the size of z is smaller than the size of Sk times exponential minus distance from z to z prime square over 8k. Why is that? Because you have z prime, and you define the function which is basically the signed distance between z and z prime. So it's 1/2 the distance from z minus 1/2 the distance from z prime, say. So this function is at least dz prime over 2 on z. It's at most minus dz prime over 2 on z prime, and the average is 0 by symmetry. Well, so here there is no symmetry here, but I want to apply this with y and y bar, and with y and y bar you have symmetry, so you know that the function is somehow centered. And so then you have a Lipschitz function which take large values on two sets. According to this definition, it means that those sets do not have a very large measure. And so now you know concentration of measure in the symmetric group. This descends, this goes down to the set Ck by some measure, by some abstract nonsense. You have a Lipschitz function on Ck, you lift it to Sk by choosing an origin, and all fibers have the same size, so the uniform measure on Sk is sent to the uniform measure on Ck, and this works. And in the end, you get that the relative measure of y in Ck, here you have, in the end, you get that the size of y is smaller than the size of Ck times exponential minus the distance from y to y bar, but this is at least the distance from A to B, square over 8k. And of course, this depends on k. K was the distance between m and m bar. It's also the distance between point A and B's. And so the worst value is for k. It's a distance in the cube, so it's at most n. And so the worst value you get is when k equals n. So the alpha here, you get alpha equal, and you have to take a square root at some point, you get alpha equal exponential minus d a b square over 8n. And when you take the logarithm, it gives you, and take square roots, it gives you the original inequality. So in the remaining 5 minutes, I'll give you a generalization of the final theorem. Because when there is one point in common between A and B, then the distance DAB is 0. That's not very nice. So maybe you would like to get a stronger inequality. And also, maybe instead of sets A and B, you would like to consider measures, so weighted sets, in which some points are more important than others. And so you would get refined inequalities. So it's an entropy version of the inequality. So now I'm going to take two measures, mu A and mu B, two normalized measures, so probability measures. On the discrete cube. So the typical example is mu A equal 1A over the size of A, and likewise for mu B. So that's the this way you will get the previous statement. And now I have to define a weighted set of midpoints. So define a random midpoint. Okay, no. So for fixed point A and B in X, you define the midpoint measure of A and B by taking the uniform, by taking one midpoint of A and B at random among all possibilities. So you define mid of AB to be the uniform measure on all midpoints of A and B. With t equal 1/2 again. So it's exact midpoints. And now you define the midpoint measure of mu A and mu B by integrating for A in mu A and B in mu B independently. So you get all crossed midpoints. Define the midpoint measure of mu A and mu B by bilinear combination mid AB, mu A of A, mu B of B. So if mu A and mu B are uniform on sets A and B, you get the uniform measure. Not exactly. No, you get some measure supported on the midpoints, on the classical midpoints of sets A and B, and it's It's not uniform, so you may find some midpoints more frequently than others. And this leads to an improved inequality, by the way. Now, for a measure on the set X, what's the equivalent of the cardinality of the set? Well, for a measure, it's the Shannon entropy. Well, the Shannon entropy is the equivalent of the logarithm of the size of the set. So let S of mu it's minus the sum of mu of x log mu of x, the Shannon entropy. Then the theorem is that the entropy of the set of midpoints of mu A and mu B is at least the average of the entropies of mu A and of mu B plus k over 8 times, and this time you get an improved inequality with the transportation distance W1 between mu A and mu B squared. And this is, of course, always at least DAB if mu A is supported in A and mu B is supported in B. Squared. Okay. And I'm not going to give you the proof. Well, the proof follows the same line, but it's more technical because you have to deal with entropies. So basically, instead of using the cardinality of fibers y and the constant alpha, instead you use the decomposition of entropy for products. And then the big difference is how do you get the correspondence, the transportation distance instead of just the minimal distance? Well, you can observe that actually it's on top yet. Each time you get a correspondence between C and C bar prime, it gives you a correspondence between A and B prime. And so there is an equivalence between couplings on measure between the measure y and the measure y bar, and couplings between the measure mu A and the measure mu B. So if you do a refined version of the isometry of the coding map, you get a coupling between mu A and mu B instead, and that's how you get the refined inequality. Thank you.
I have many questions.
Okay, so maybe for the shorter questions first.
Well, over there, you have the tensor product, mu and I and mu and B.
Yeah.
But given mu and I and mu and B, I have many, is a fiber bundle that you have cooperated mu, that you can write down a mu over there and then it change over here your middle mu A and mu B. Do you understand me?
No, there is no choice here.
Yeah, you define in this way,
yeah.
but you could define in a different way.
Yeah, sure. So, for instance, the ideal, what we would like to get is here, we would like...
The midpoint.
Yeah, we would like to get the optimal, replace this tensor product measure by the optimal coupling.
The optimal in what sense?
Say, in the sense of transport. So that would be what we would like to get.
Prove it.
No, we don't know how to prove it, but this was our goal. We wanted instead to define a smaller set of midpoints, because this is the biggest set of midpoints you can get, and we wanted to get a smaller one. And of course, in that case, the theorem would be stronger. But so what we want to have here is, instead of the tensor product of the measures, which amounts to taking all pairings of A and B, we would like to get only the optimal pairing. And so it's here that you get the difference. Yes?
I have 2 questions. What's DAB? Sorry, just how do you define DAB?
Oh, DAB is the minimal.
The minimal one.
Yeah,
Oh, right.
it's this.
Okay, thanks. And second of all, is there any reason why you get the W1 instead of W2 in the Riemann case?
Yes. Concentration of measure, like this Gaussian type of inequality, is equivalent, by a theorem of Bobkov and Goetze, to an inequality between to an inequality involving on one side the entropy and on the other side the W1 distance. And it's because both have the same nice behavior under tensor products, basically. Okay, and this is very fundamental. In discrete spaces, typically everything you're going to try and try to write with W2 will not work very well in discrete settings.
This may be very related to this question. The Riemannian case, or even in Gauss space, you have W2. So is there a way of using some central limit theorem there and then get something for the Gaussian, or is it the same?
I don't know. Maybe I think that's a good idea, but I don't know.
Yeah,
But if you have many questions, you ask them in
Let me
private
ask you a
afterwards.
question. You have 0, 1 to n. This implies to have a number in a rational number in binary development. Now, if you change base, is this your theory is invariant to the change of base?
Probably not.
I see.
Okay, so let's thank